All right, so today is our class number 15. We're going to continue our journey in support vector machines. We are sticking to this regression part now. So in general, we call them support vector regressors, but as we said earlier, both classification and regression, we call them generally support vector machines. All right, so let's see how can we distinguish the idea of classification versus regression when it comes to support vector machines. The idea of SVM classification can be easily transposed to regression problems. However, you should be careful that the role of the margin is different. So the way that we define margin in classification is going to be different here when we are doing the regression analysis. The objective is to basically find a hyperplane. So here in this case, this is my hyperplane that holds the maximum training observation within the margin. So this margin that you're defining is our tolerance level, right? And we set this tolerance level to a fixed number. It's not going to be a hyperparameter. Okay, don't confuse this one with a hyperparameter. This is going to be a fixed number, and we can play around with it. But usually by default, you pick a number for that. And in Python, I think I don't know. You're going to check it out. It's not off the top of my head what's the exact that number. But we fix that number, and then the algorithm is going to go ahead and find the W stars and B stars to finally pin down this F hat of X, right? So that's the goal, right? And so let's see how we can start from the very simple case of support vector regression. Remember, in classification, we started with MMC, right? And then we said if the data is noisy or there are a bunch of outliers, we have to go from hard margin to soft margin. And then if the data is nonlinear, we have to go from soft margin, adding the kernel part to that, right? In regression, it's exactly the same story. We're going to start with the very simple one, but sometimes there is no solution to this optimization problem that you're looking at right now. So we have to go beyond that. Basically, we're going to add the slack variables. And then sometimes we need to add some nonlinearity. We do that by doing kernel tree. So the path is exactly the same as classification. But again, the way that we define the margin is slightly different. What I want you to pay very good attention is that look at the axis here. We have y versus x, right? So it's not x1, x2. So you can basically these are the target variables. You can find the value of the target variable. So for example, this is your y1, y2 in 2 dimensions, right? Then let's see what we have. So here we're trying to minimize the weights. And we talked about this one, minimization of the weights that are equivalent to maximizing the margin, right? So this is basically if you're looking at this margin, so you can treat it the same way. However, the constraint is different. So the constraint here, actually it's really straightforward and easy to understand. We're gonna say that the yi's minus y hat, this is my y hat, right? It should be less than epsilon. So this is yi minus y hat. Does everyone see that? So y is the true value, minus y hat is the one that the model is predicting, right? So this is the model that's predicting. This is the value that the model is predicting, and etc. Right? These are the predictions. So y minus y hat should be less than this threshold that we define as epsilon. Is the first constraint clear? Y minus y hat should be less than that epsilon. Okay, so for the second one, this y hat minus y, so the ones for the observations that are below the hyperplane. So for example, this one is y hat minus y. Does everyone see that? Y hat minus y, again, should be less than epsilon. So this is our epsilon. So these are the constraints, right? So basically, the algorithm is going to try to find the weights such that the majority of all the observations are within the margin. In this case, there is a solution. So if you do this optimization problem, then there's going to be a solution, and the algorithm is going to give you back the W star and B star, we're done. However, imagine there's a couple of observations here. You have an observation here, and there's an observation here, right? So it seems that if you fix your epsilon, then the algorithm is not find that hard margin, think of it as hard margin, right? To fit all the observations within that margin. Is that clear? Okay. So what's the solution? Exactly like going from MMC to SVC, here we go from kind of analogous hard margin to soft margin. I need to give me some slack, add these slack variables. Yes?
I guess I'm just a little confused. Maybe I missed it. So is this margin trying to fit all of the data inside the margin?
Yeah, exactly.
Wow.
Well, because you don't want to come up with a simple. Well, let's say this is your data. I don't know. The data is nonlinear, right? Then we define this margin such that if the margin, I don't know, do something like this, if it's basically trying to follow the pattern of the data.
Yeah.
So for that reason, the more observation it can fit within the margin, the better news. But sometimes it's not feasible. Again, this doesn't happen in reality most of the time. This is very simplistic version of it because we know that there is going to be a bunch of observations here, and it doesn't worth to think of this to widen that epsilon, because if you widen that epsilon, it doesn't make any sense, right? You always get the average, so the average is going to be the prediction. Okay, so that's why we're going to say a good fit or a good model is the one that's holding the majority of the training observation within the margin, right? Maybe not all of them. So it's not possible to always fit all of them within the margin, like this one. So for example, so this is exactly the same as adding a little bit of bias in order to hope that the variance is going to reduce. Exactly the same story. Here, by introducing the slack variables, we hope that by adding a little bit of bias, then the variance overall is going to reduce and the RMSE overall is going to decrease, right? So here, if you look at the model on the right-hand side, we are going to from, again, this is analogous. In regression, we don't necessarily call it hard margin, soft margin, but this is analogous to hard margin, soft margin. It's going from hard margin to soft margin by adding the slack variables, right? So here it says that, okay, hey, algorithm, I want you to allow for some observations outside of the margin, okay? So this is equivalent to misclassifications. You know, slack variables in classification, we call them the number of misclassifications. In regression, this is the number of observations or the distance of observations outside of the margin, right? So this is how we define the slack variables. All right, the constraints are going to be almost the same with a little change, right? So for example, the ones that are above the hyperplane, we say, let's look at this one. It's going to be yi minus y hat should be less than equal, not epsilon anymore. I'm adding for a little bit of a slack too, right? Should be less than and a slack plus the error. So basically, I'm allowing for some observations to be outside of that margin, okay? And the same story for the second observation, right? For the second constraint. And this is, I just showed here for two slack variables, but in general, we can just write them as summation of the absolute value. So people use L1, so this is L1, absolute value of xi, let's call it xi I, and or Python, by default in Python, is using L2. So it's a summation of xi I to the power of 2, okay? So by default, when you do, when this sees this penalization part is introduced to the model in Python, by default is using L2 norm of the slack variables, right? So here, what I'm showing you here is that basically I assume that xi and xi star are positive, and then I'm simply adding them up together, and then I'm penalizing it, okay? Because you have to make sure that everything is unchecked, right? So you don't allow for slacks without penalizing them, right? So this is exactly what we're doing. We are allowing for some slacks in the model, but we have to penalize them. Okay, so this is our hyperparameter tuning that we need to tune, right? So yeah.
Is C chosen just by the
Yes, this is exact. So this C is a hyperparameter, and this is exactly like the cost of misclassification, but here's the cost of slack variables, right? And so the interpretation is pretty much the same as classification. So let's give it a try. If C is high, what will happen to bias? What will happen to flexibility of the model? Imagine C is high. If C is high, what does it mean intuitively? It means that the model does not allow for large slacks, right? So the slacks should be smaller. So if the slacks should be smaller, when does that happen? When the model is more flexible. When the model is more flexible, what's the bias? Smaller, exactly. So the same story. If C is high, bias is small, variance is large. You can think of it as more flexible margin. right? Now, and the opposite is the case. If C is small, bias is going to be higher and variance is going to be smaller. I want you to think about this case. What if C is equal to 0? What does that mean? Yeah, if C is equal to 0, you're not penalizing the slack variables. So if you're not penalizing the slack variables, they can be as large as possible, right? So what does the model get? So if C is equal to 0, the model is going to always predict Y bar. The bias is going to be the maximum, the variance is going to be the smallest. And you're going to see this in Python next class. So is the concept clear? All right.
And when you say Y bar, you aren't saying an actual like horizontal line, just the
I actually mean horizontal line Y bar. Yeah. Because well, I'm glad that you talked about it, because if you look up the documentation of the C in Python, you will see that it's written something like this. C is equivalent to inverse of regularization parameter, right? So what does it mean? It means that, and regularization parameter, I want you guys to think about, the penalized regression. When we were penalizing, when we added the L1 version of the weights or L2 version of the L2 norm of the weights, we were penalizing the weights. Do you remember that? So for example, in Ridge or Lasso, we were penalizing the weights. It means that getting rid of the exponential variables from the model. So C in SVR is inversely related to regularization. It means that if C is equal to 0, that regularization is max. If penalization of the variables is max, so the coefficients are going to become 0. Does that make sense? So that when the coefficient is 0, the models always get Y bar. Very good. Okay, now you're going to say that, okay, so if I add the slack variable, it can handle these observations, right? So but by going, again, analogously, going from hard margin to soft margin, adding slack variables can handle this kind of data. But what if the pattern in the data is completely nonlinear? So maybe that slack variable is not enough. We have to use the kernel trick to do exactly the same argument that we had in classification. The kernel trick is able to handle the nonlinear data, right? So, and the optimization for the kernel trick is this. We're going to minimize these weights and by considering a slack. So again, in this example, I have 2 slacks, but guys, don't think that there's only 2, xi and xi star. There's a bunch of, as long as I have observations outside of the margin, I have these xi's and I can call them xi j in general. And this can be L1 or L2, it really doesn't matter. Right. And I emphasize again one more time, by default in Python, it's using L2 norm. And then the only difference between this optimization and the previous one is that instead of linear relationship between the W and X, so instead of W1x1, W2x2, we're using a kernel function, right? And that kernel trick, as a reminder, you can think of it as a function that's without going to higher dimension, it's as if synthetically it's transforming the data in higher dimension and find the hyperplane and then project the data back in the lower dimension. But the kernel trick does that without going to higher dimension. Okay, so that's the beauty of the kernel tree. And the constraints are the same, right? So for example, let's look at the first one. So what is this one? This is my f hat of x or y hat minus my y. So for example, this is the ones that predictions are greater, right? So like this one. So this is my y hat, and this is these are the y's, right? For 2 observations. So y hat minus y should be less than or equal to epsilon plus xi star. And the other one is y minus y hat. So let's say this is y minus y hat. So y hat should be less than or equal to epsilon plus xi I. So I hope that everyone so this is my epsilon, this is the xi. Is that clear? Very good. Okay. And so this is really interesting, actually. It says that the goal in kernel SVR is to minimize the sum of the square of weights, right? Minimize the sum of square of weights, subject to errors being small. So if you reverse this statement, it should ring a bell, right? So if I say that instead of minimizing the sum of square of weights and subject to the errors, if I say something like this, minimize the sum of square of errors subject to weights, what is this? We have seen this before. minimize the sum of square of errors. So what is minimize sum of square errors? Simple linear regression model, right? So what is minimizing sum of square of errors plus the cost function of the error of the weights? What is that one? L1 version of the weights, L2 version of the weights. This is penalized regression. Do you remember? We were minimizing, so it says that basically the second bullet point says that this is somewhat the opposite of the penalized linear regression, which seeks to minimize the error subject to the weights being small enough. So let me remind you, if I'm minimizing the MSE, this is simply my linear regression model, right? Simple econometric OLS sort of things. If I minimize the MSE plus lambda L1, what is this? And L1, remember, I remind you that it was the summation, L1 was the summation of absolute values of WIs. So what is this one? This is lasso, right? This is lasso. If it is minimizing MSE, oops. If the objective function is minimize MSE plus L2, well, lambda L2, what is this one? This is our ridge regression, and a combination of the two was our elasticness, right? So do you see that somehow the optimization is the reverse of each other, right? So here we are saying that minimize the weights, given we have a small set of errors, right? In penalized regression, it says that minimize the errors, and for a fact that we want to penalize the weights. So that's somehow the other way around. But I think that's an interesting observation. All right, are we good in terms of theory of the support vector regression? And what do we mean by margin here? All right, and then we can simply, let's look at some examples, right? So for example, the data, the real data are the orange dots. And if I use linear model, so not surprisingly, we get something like this. This is literally very close to our simple linear regression model, right? And polynomial, again, is going to be the blue one. Well, of course, it's going to be, polynomial models is, so we had we talked about 4 different kernels, right? Linear, polynomial, RBF, and sigmoid, right? So polynomial is simply, polynomial trick do the job by simply adding the polynomial coefficients to the model, right? If I have x1 and x2, it's going to add x1 square, x2 square, and interaction between x1 and x2 to the model, and then calculate the weights and do the job, right? RBF kernel, however, is going to calculate some similarity between observations by doing the dot product. So what do I mean by similarity of the observations? So for example, I have 2 observations. It's going to calculate the dot product, find the distance of these 2. And if they're close to each other, it will assign a small number to that. If they're far from each other, it will assign a large number to that. Actually, in reality, it's the other way around. If they're close to each other, the number is going to be larger. If they're far from each other, the kernel is going to be smaller, right? So that's how the RBF kernel is doing the classification or regression in this class. And so I think it's understandable. Well, we can understand all these lines. And as you can see, for example, for the RBF is doing the best job. It seems that it's doing the best job here. And we're gonna look at some decision boundaries and comparing classification models. And usually for the data sets that we work in finance and econ with, usually RBF is the winner. Okay, so it is safe to start your analysis by simply using the default values in Python, and the default kernel in Python is RBF. There's a reason that the default kernel is RBF, because if you take the majority, no, I don't know, if you work with different type of data sets, RBF is the winner. And let's look at that one. Let's look at the idea of why the RBF is winner. And for that, we need to talk about, make sure that we understand the hyperparameters, and how we can tune them in Python, let's say. So what are the hyperparameters? And this is, guys, the rest of the slides are both for classification and regression, okay? So when I say C, it's a cost function in classification and the cost function, not the cost function, cost of misclassification and cost of slack variables, okay? And so this C, we can think of it as cost of misclassification for classification analysis, or cost of adding slack variables in regression analysis. It controls bias versus variance trade-off. And we know that if C is large, then we're going to deal with the narrower margin, and that's how it's going to impact the bias versus variance, right? So if the margin is narrower or C is larger, the bias is going to be smaller, and the variance is going to be larger. What can I say about the overfitting and underfitting? If the C is large, am I overfitting or underfitting? If it, let's say C is super large, you're overfitting, right? Okay. The next hyperparameter is kernel function itself. So we know that at least the four most common ones are sigmoid, RBF, polynomial, and linear. And these are the ones that in scikit-learn package, you can find them, well, you can simply apply them. If you want to come up with a customized kernel, you have to code it from scratch. But if you want to use either of these four kernels, you can leverage on Python, a scikit-learn package. Then the next one, gamma only applies to RBF. And the reason that I bring it here because there's a good chance that at the end of the day, most of the models, most of the data sets that you're dealing with, RBF is doing a good job. So you should know what is gamma and what does that mean. So I think we talked about that one, that gamma is inversely related to sigma square, right? And so, and sigma square, I don't know, this is simplistically for one variable, but if I have two classes, it's multi-variable Gaussian distribution function. Here, let's say for sake of argument, there's one variable. So basically sigma is, let's say, our standard deviation, right? So if sigma is large, let's do it this way. If sigma is large, so it means that the distribution is wider. And what can I say about gamma? Again, if sigma is large, gamma is small, right? When gamma is small, we are reaching out to closer neighborhoods, right? So it's like something like this. Look at that. When I increase the, gamma is, oh, sorry, the other way around. If sigma is large, we are reaching out to further points because it's, the standard deviation is higher, right? So if gamma is small, we are reaching out to further points. So look at that. Basically, we are using one, let's say this is one landmark in our RBF, and it's going to basically reach out to this observation using the same landmark, right? But if I'm increasing gamma, if gamma is increasing, it means that sigma is decreasing. So we are looking at the data sets more locally. So for each of these things, these observations that are locally located within the data, we come up with a separate landmark, right? And then basically we are reaching out to closer observation. We classify it like this. Does that make sense? Okay. So in this example, when gamma is equal to 0.1, this is a misclassification, this is a misclassification. But in this example, when gamma is equal to 10, there's no misclassification going on. Okay, are we good? All right. Okay, now, by the way, you can replicate a bunch of all these things. So I put a link down there. So most of the thing that I used was directly coming from Python documentation, which are all replicable. So just give it a try for fun. Just look at if you can replicate these graphs. And so now let's say we have three hyperparameters. Usually we have three hyperparameters that we need to tune in SVM or SVM in general. How can we do that, right? There are three of them. There's not only one. So this is a very painful process. The good news is that you don't need to do it. Python does it for you. But the bad news is that it is very computationally heavy. And actually, I'm putting together a notebook for our next class. And so historically, I used a very small data set, 500 observations. And this semester, I was just giving it a try using that bike share observations, right? Which is 17,000. And it's taken a long time to do the grid search. So that's the downside of the grid search. But let's see what is grid search. So basically, what we're going to do is call grid search cross-validation to tune the hyperparameters. And maybe it sounds complicated, but the idea is very simple. Let's say I'm going to make a grid. Literally, I'm going to make a grid, and that I call it grid of, I don't know, we call it param grid, right? And I literally make a dictionary. I say that, okay, what do you want the kernel? What do you want me to explore for the kernel, right? Say, okay, explore the linear, RBF, and polynomial for me, right? So let's say I put these three in this dictionary, in parameter of the grid of parameters, right? So I want to explore three of the kernels. I want to explore 4 different values of C. I want to explore 1, 2, 3, 4 different values of gamma. And for cross-validation, you can do, for example, you can do 10-fold cross-validation, 5-fold cross-validation, and etc. Right? The reason that we're using cross-validation is an old story. You're using cross-validation because you don't want to cheat, right? You don't want to train the model. You don't want to look at the performance metrics only by using the training data. It's not fair because obviously you're going to do a good job. On the other hand, you don't want to use the test observations because sometimes you don't observe them literally. And more importantly, you don't want to find the hyperparameters of the model by leaking information from the test set. Because we use the test set to do performance measures, right? Not for updating the model. That's definitely not fair. Okay. So how many combinations do I have? Let's say I want you to think about it. If I have 3, I don't know, 3 versions of kernel, 4 values of C, and 4 values of gamma, how many combinations do I have? 3 multiplied 4 by 4, right? So here, so far we have 48. And then if I use 10-fold cross-validation, then it's going to be add up to 480 times that the model, the SVM, should be run over the data set, right? And now let's assume any of these folds has, let's say, 10,000 observations. So 10,000 multiplied 400 is 480 is 480,000 time that the model need to, well, 48 loops and then repeat that process 10 times. So 480 times calculate this SVM. So you can see it's computationally super heavy, right? It is very heavy. And beside that, who says that go from 0.1 to 1, right? So why not 0.2, 0.3, 0.4? So as you can see, it's really usually, it's not easy to use grid search, cross-validation, and find the optimal values of hyperparameters, right? But regardless, we're going to give it a try because there's no alternative here, right? Especially if the data set is small, that's fine. You can, I don't know, you can try a bunch of them within an hour. But if the data set is large, I have a computer at home, which is the RAM is 64, and the CPU, I think, is Core i7. Everything is perfectly fine. But it's for this observation, for this data set that I'm working with, which has 17,000 observation, each round is taking 20 minutes, okay? And it has to go over I think I'm trying 137, 35-ish different combinations. So I let it running from last night and then still it's not done. Well, right now I'm trying Google Colab in my office using a GPU and see which one is faster. If that's faster, maybe I'll introduce you to Google Colab as well. Do you know what is Google Colab? Yeah, you can run all these things on Google Colab. Basically, that's the service provided by Google, and then you can use their GPUs and TPUs, and it's supposedly it should be faster. All right, so yes.
Would you say that gamma equals 10 is overfitting?
Well, in this case, actually we have to, in this case you can say, yeah, because there's a good chance that the test set is something like this. You can say it's overkilling it here, yeah, or overfitting, yeah. Yeah. But usually we don't judge visually. Does that make sense? We look at the performance matrices and then see, okay, if it is, so for example, how can I say that by looking at 2 numbers that if I'm overfitting or not? So this is classification, right? So I look at the accuracy. If the accuracy in the train set is 90% and the test set is 10% or 20%, it's absolutely overfitting. Okay, but if they're close to each other, so it's a sign that it's not overfitting. Okay, guys, remember in real world we don't have the luxury of observing these things, right? So the problems that you're dealing with are very high dimensional, or at least relatively high dimensional, and we cannot visualize things like this. All right, now let's have some visualizations together. So first, I want to use SVM. So in this slide, I want to use SVM. In the next slide, we are going to compare SVM versus KNN versus different kernels of SVM. So here, we're focusing on SVM, and this is classification. And we wanted to compare four different kernels, right? So linear, RBF, polynomial, and sigmoid. And so let me walk you through a little bit of what are these. And by the way, all these things are replicable in Python documentation for scikit-learn. You can find the codes here over the link. So the circles obviously are the data. The solid red ones, or the solid ones in general, are train observations. The more transparent, do you see the difference? Some of them are more solid than the other ones. Well, I think the lighting here is not perfect, but some of the red circles are more solid than the other ones. So the solid ones are train sets, and the, let's call it, the pale ones are test set. The same story for blue ones. So the solid blue ones are train observations, and the pale ones, let's say, are tests. It really doesn't matter, if you want to distinguish train versus test. I think if you just focus on red versus blue, it's going to do the job, right? So let's focus on red versus blue, right? Look at this one. Look at the first box, right? So our first box, it seems that the data is not necessarily linear, right? So it's like two moon in each other. So actually, this is a famous data set. It's called moon set, something like this. So you can think of two moons within each other, right? And so this data set is nonlinear without looking at the answers, because you can see the answer. Which kernel do you think is going to do a better job? At least tell me linear kernel versus nonlinear kernel, right? Most probably the nonlinear is going to do a better job because, not surprisingly, the data is nonlinear, right? And the numbers here on the bottom right are the accuracies. So these are the accuracy. Okay. So for the first example, so this is our example number 1, and then let's call them 2, 3. As you can see, our hyperplane is something like this because we are using the linear kernel. And I want you to, for now, ignore the colors of the background. The idea is that the more darker they are, the further you are from the hyperplane, and less dark. But in general, again, I want you to think of them as blue versus red, right? So at the background, we have blue versus red. The dots themselves are blue versus red, right? So it seems that basically here, linear SVM is doing a decent job, right? The accuracy is 90%. And RBF SVM, look at that, how beautifully it's able to capture this nonlinearity here. And the accuracy is 97%, right? And then polynomial SVM, actually, basically, if you add the polynomial version of the variable to the model, surprisingly, it's doing worse than the simple model, simple linear model, right? So it's 80, and this is not surprising. This is, for many of the, at least the data sets that I have worked with, more linear SVM is doing a better job than polynomial. Okay, so we usually pick the RBF because RBF most of the time is the winner. And then sigmoid SVM, again, sigmoid, if you remember that 3D picture of the sigmoid kernel, so this is, you can think of it as a projection. And so it seems that this is doing a very bad job. These are completely misclassified, completely misclassified. Are you following the misclassification? No red dots on the blue background or blue dots on the red background, right? So accuracy is 75. So here for the first one, the winner is RBF, right? The second observation, again, without looking at the answer, definitely the winner is going to be RBF, right? Because this data set is designed for RBF, having a multivariable Gaussian distribution on top of it and then do the projection. This is exactly designed for that, right? So not surprisingly, the RBF is doing to do a very good job. And look at the linear one, because regardless of how I divide this data set, the linear model is going to do a very poor job, the accuracy of 47% only. There's no way to skip this, to solve this nonlinearity using a linear kernel, right? Again, polynomial SVM, again, not surprisingly, because you're just adding polynomial features to the data, it's bending the line. So you cannot come up with circles, closed circles in 2 dimensions, right? So you're simply bending the line. So regardless of how I bend this one, at the end of the day, I get a lot of misclassification at one side, right? So this is going to perform poorly. And finally, sigmoid. For sigmoid, remember, the projections are something like this. So sigmoid is doing a relatively better job because I can say within this, call it blue, outside of it, call it red. So that's why the sigmoid is doing a relatively good jobs, relatively 60% accuracy, okay? Again, the winner is RBF. Then finally, if the data set is something like this, so it seems to me that linear model should do a perfect job, right? Because this is not a complicated data. And as you can see, the accuracy of the linear model is 90%. But even when the data is linear, RBF is going to outperform that. Okay. So RBF is outperforming that. And again, polynomial surprisingly is doing a bad job, most probably because we are, I don't know the degree of polynomial here in this example, but most probably this is overfitting. And sigmoid is able to do a decent job as well. So again, the winner is RBF. So what's the lesson learned? If the data is linear or nonlinear, the winner is RBF, right? So you can safely, for most applications, you can safely use RBF unless you are working in 2 dimension. You can literally observe the data or you have some prior belief that the data should behave strangely at tails or things like that. So for that case, you come up with your own customized kernel function, right? Which is way more advanced way out of the scope of this class. So in this class, we're going to focus on RBF kernel for the majority of the applications. All right, are we good? Okay, so here's the exercise for you. So imagine this is the data set, right? I want you to compare KNN and linear SVM and RBF SVM. Which one do you think is winner for this one?
Probably RBF.
And so guys, remember, KNN should do a perfect job here because what is the dimension of the data, the feature space? 2. So when the feature, we are not dealing with the Kirchhoff dimensionality or something like that. And we know that kernel is very good, the KNN is very good at fitting when the data is noisy, right? So here the data is not noisy, but I just want you to keep in mind that KNN is powerful and the dimension is low, right? So most probably KNN and RBF are going to do a good job, and not surprisingly, linear SVM should be the worst performer, right? So, okay, I was a little misplaced. So here, kernel, linear SVM. Look at the accuracy. KNN, 82%, linear SVM, 75, and RBF, 88. So KNN is surprisingly powerful, right? Again, because the dimensionality of the data is small, and we know that kernel is powerful, even though it's super simple. You know, kernel is a non-parametric model. It's super simple, but look how beautifully it's able to capture.
Are there instances where KNN could do better than RBF? Or do you think RBF is also going to?
Time-wise, yes. Let's say the data is, it's a good question. So if you didn't hear at home, so Abraham is asking, are there cases that KNN is doing a better job than RBF? I can say time-wise, yes, if the data is low dimension and sample size is large. Because when sample size is large, SVM is not fast. Okay, so SVM is designed for small to medium-sized samples. But KNN, if you have, I don't know, very large samples, but only the dimension is 2, is going to do a decent job. All right, next one. So look at the next data set. Which one is going to do a better job? We already know that. We already look at this data set by the performance of the RBF, right? RBF is doing a decent job. But what about KNN? Again, should do a good job, right? And of course, the linear one is not going to do a good job. So linear definitely is a loser here. But KNN, again, is doing a relatively good job, around 80% accuracy. And then finally, if you have something like this, so most probably all of them should be doing a good job, right? So either KNN or even a linear. I think a linear classifier to me seems doing a perfect job here. So let's look at the numbers.
So linear is going to be less computationally expensive, right?
No, that's beyond the scope of this course, but I can talk about it. Well, the beauty of RBF kernel is that, so let me clear this one, but this is, yeah, let me talk about this one, but the answer is no. So the KNN, the accuracy is 97%. RBF, again, 97%. So Abraham, to your point, and linear is 88%. So this is a very good question. Ryan is asking, computation-wise, linear should be, I don't know, simpler than RBF, right? The answer is no, because RBF is able to handle even infinite dimension. And by calculating the dot product, it's a little, well, let me talk about it. At the end of the day, it's going to calculate the dot products between every two pairs of observations. And when it comes to higher dimension, calculate that in all the dimensions, right? But the thing is that RBF, and there's a coefficient beyond this, before these dot products. In RBF, when the dimensionality is, let's say, thousands, it's super, very smartly is going to converge many of these alphas to zeros. So it's going to get rid of them when it's come to calculation. But linear SVM, you have to go through all those dimensions. So actually, this is the Python notebook that I'm working on. You can look at the time of each of these different combinations in the grid search. The linear kernels are going to take a lot more time than the RBF. The reason is that the dimensionality of the data is relatively large, right? So I'm working on the bike-share data set. I think it's around 50 something if you if you use dummy verbal for everything you have in the model. And then the linear one is going to do is going to take a longer time. We have 17,000 observation, dimension of the data is large. So RBF, it's very powerful. The theory of RBF is very beautiful. All right. Okay. So we're done with the, at least with tuning hyperparameters. I think we have a good understanding of the intuition. And when it comes to application, we just trust Python. If you want to work with any kind of custom kernel, you have to code from scratch, right? So now let's talk about K multiple class SVM. Remember, guys, we said that SVM by construction is designed for two-class classification, right? Why? Because that's how we define the hyperplane. A hyperplane is I don't know, the dimension is one less than the surrounding space, and it's going to divide that space, we call it ambient space, into two subspaces, right? So that's why by nature, we said that the SVM is designed for two-class classification. If I have three classes like this, we have green triangles, red crosses, and then blue circles. So let's call them green, red, blue. If I have three classes, how can SVM do the job, right? The answer is that there are two methods. Number one, we call it OVA, one versus all. Number two is OVO, one versus one, right? So in the one versus all, these are the steps. We have to fit K different, in this case, three different, K different two-class SVM classifiers. And we say each class versus the rest of the classes, right? So for example, look at that. K is 3, and I'm looking at the green. So I'm saying that green versus everything else. Blue versus everything else, and red versus everything else. Does that make sense? So we divide them into two-class classification, right? Now, if I say green versus everything else, I can go ahead and run the SVM, come up with the hyperplane, right? Does everyone agree that this is the hyperplane? I can call it F hat. Let's call it F hat green. Are we good? Okay. Then let's call this one F hat of blue. All right, let me erase the extra stuff. And what about this one? Most probably something like this, right? I don't know, maybe even a little tilted toward. This is my F hat of red. Does everyone understand how the algorithm is working? So one versus everything else. And now I can plot them all on top of each other. So let's say something like this. Pay attention here, because when it comes to this decision criteria, it's going to be a little tricky. So this is my F hat green, and then I have something like here, F hat blue. Then we're gonna have, let's say, this is my F hat red, okay? So at the end of the day, we have something like this. Then we're going to, so what's the goal? We want to throw some new data in the test set to the model and see what is the class of that data, right? Let's say I throw a cross here. The model Biddle classified as red cross, right? Or classified as red, right? So if I take observation here with these features, X1 and X2. So let's say this is my X test. How do we find the winner? So we have to go ahead and calculate f hat of green using the X test set and compare it to f hat of blue using the X test set, compare it to f hat of red using the X. Which one should the algorithm pick? You can cheat and look at the answer, but conceptually, well, let me give you the answer. You think about why. So the answer is we have to come up with some numbers, right? Let's say 3, 2, 1, I don't know, 5 minus 2 minus 1. So the winner is going to be the one that has the largest f hat, right? So I want you to think about it. How should I interpret the f hat? What does this f hat mean? Basically, I want to explain why the winner, and when I say the winner, it means that the algorithm is going to classify it as that class, right? Is going to be the one that has the largest f hat. So the answer is going to lie on the concept of f hat. What do you think is the answer? Guys at home. Okay, so Abraham is saying probability. Remember, SVM does not generate probability. The outcomes of SVM are non-probabilistic outcome. That was a good.
Is f hat measuring distance from each one of these vectors?
Awesome. Yeah. Ethan, is that you?
No, that was Tommy.
I know that's Tommy. Very good answer. Well, basically, f hat, as you said. Oh, okay, let me see. Very good answer. So f hat is the distance from the hyperplane, right? The further you are from the hyperplane, the more confident you are that the observation belongs to that class, right? So far, I think everyone is on board, right? Now, let me visualize these distances, and then you're going to get a little confused. So are we good in terms of why the largest f hat is going to be the winner? Because it has that observation is furthest from the hyperplane, the separating hyperplane. So for that reason, we're going to call them, in this case, we call it, for example, class red, right? So let me be consistent with what I put there. So I want the red to be the winner. So let's go ahead and calculate those f hats. All right, so let's look at this observation in the test set. So what is the distance, perpendicular distance from f hat of green? So that's this one. What is the perpendicular distance from f hat of red? That's this one. What is the perpendicular distance from f hat of blue? This is this one. Which one is largest? This is the part that you're going to get confused. Which one is largest? So all of us may think that the largest is blue, right? But the algorithm better classify it as red. So what's going on here? Guys, the points right on the hyperplane, what's f hat? Right on the hyperplane. 0, very good. The point to the left, does everyone see that f hat is greater than, so for the green, f hat is greater than 0 to the left of the hyperplane? But what about to the right of the hyperplane? F hat of green is going to be a negative number. Does that make sense? So f hat of green here, it's going to be, let's say, -4. F hat of blue, the same story, minus, let's say, 6. F hat of R, plus, I don't know, 1 or 2. Which one is the biggest? What's the class? Red.
So it's not absolute value.
Yeah, the sign matters because you're on the right side of the hyperplane or wrong side of the hyperplane. So for green, so here for green and blue, we're completely on the wrong side of the hyperplane.
So that really comes into effect when you get put into, say, the bottom right corner where it's in between the blue and the red.
Here?
Yeah, like right there.
Yeah, it's going to be classified as blue because it's on the right side of the blue.
Well, isn't it on the right side of the red also?
No, no, oh, yeah, both of them. Yeah, for that one, yeah, you're good. So yeah, for that one, we look at the distance. Which one is closer?
Yeah.
Yeah. But the idea is that, do you remember in SVM, we said there's a reason that we call them +1, -1. So that's the reason, because we want to keep track of the sign and the magnitude. Okay. All right. So this is how the one versus all is doing the job. And how can I apply it in Python? It's super easy. Just you add a feature, OVA or OVO to the function. Okay. As you can guess, applications in Python are very easy. So your job is to learn the concept, the intuition. Okay. So that was the one versus all. Not surprisingly, instead of doing that, I could have compared each of these pairs with each other, right? So for example, green, red, blue, and etc. Right? So this is the second approach. We call it one versus one. So for one versus one, there is going to be 2 out of k combination pairwise of classifiers, right? So if I have 3 classes, so let's say red, green, blue. So how many combinations can I think of? 2 out of 3. What's 2 out of 3? It's 3, right? So basically I'm comparing red and green, red and blue and green. That's it, right? It's combination, it's not permutation, because the ordering doesn't matter. Okay? Comparing red and green is the same as green and red. Okay? So if I have 5, it's going to be 2 out of 5 class. So 5, 4, 10. If I have, I don't know, 10, just think of it if you have, I don't know, 10 classes. So I just want to focus on the increasing number of these things that you have to calculate. Then 2 out of 10 is 45, right? 10, 9, 45. So basically it's increasing rapidly. This is, I have to compare 2 out of them. Let me back up a little bit. In OVA, one versus all, if I have 10 classes, how many of these calculations should I do? I have 10 of them, right? Class 1 versus all of them, class 2 versus all of them, class 3 versus all of them. So we have 10 F hats. But if I do 1 versus 1, I have 45 of them. So as you can guess, if the number of classes is small, 1 versus 1 is going to be a better comparison, but the number of classes is large, 1 versus 1 is very, very costly. So we do 1 versus all. Okay. So that's one difference. And then how do we classify? So we know that, okay, at the end of the day, we have to compare each class with another one. Let's call it L. It's really just a notation. You can call it L, M, N, whatever. 2 classes, compare 2 of these classes. And then the winner is going to be the one, the class that won the most pairwise competitions. So let's see, what does that mean? On the left, we have 1 versus all. On the right, we have 1 versus 1. Visually, does that make sense? What the algorithm is doing? 1 versus, just look at 1 versus 1. So for example, yellow versus purple, dark purple, right? So, and yellow versus green, this is going to be a hyperplane, and green versus purple, this is going to be a hyperplane, right? So we have 3 of them. Now, let's see, how do we call the winners? So we can calculate F hat of green and yellow, F hat of green and purple, F hat of yellow and purple, right? Let's throw a test observation to that data. And here, I don't care about, well, we don't necessarily care about the magnitude, because we're going to pick the one that the class that wins most of these pairwise competition. But let's see, what does that mean? So for example, for this observation, between green and purple, which one is the winner? Look at this observation. This is a test set, and I want you to focus on green versus purple. So what's the class? Ignore the yellow.
Green versus purple?
Green versus purple, and this is the observation. The class is going to be green, right? Because it's up, you know, this is the separating hyperplane. So here, anything above that hyperplane is going to be green, below that is going to be purple. Does everyone see that? We good? So let's call it green. Between green and purple. Oh, sorry, the green. Oh, so that was green and yellow. Yeah, I see where the confusion is coming from. Because I don't want to stand corrected, I said just change it I just changed the rule of the game. So green and purple, green and, I should have some power, right? Yeah. Okay, so my bad. So between green and purple, this is going to be green, right? Yeah. Between green and yellow, which one is greener? Yellow. Between yellow and purple? Yellow. So what's the majority vote? Yellow. This is how it's classified. Okay, so let's do one more. Let's do, I don't know, let's do something here. Let's call it X test 1, X test 2. Okay, first one between green and purple. Purple. Between green and yellow. There you go. Between yellow and purple. Which one is the winner? So this is how the algorithm is working, right? And again, if the number of classes is small, 2, 3, usually the 1 versus 1 is going to do a better job. Because it's, look at this one. These are a lot more clear than something like this, right? And in this case, you're completely on the wrong side. In this case, you have to look at the distance. You have to compare the distances, right? Especially for these examples like here, right? The one that you were mentioning, Brian. So in general, if the number of classes is small, you choose OVO. If the number of classes is large, because of this problem, you would be better using OVA, 1 versus all. All right, okay, we are almost there. Let's talk about pros and cons of SVM, and then finally applications of SVM in finance. Are we good in terms of concept, theory? Okay, pros and cons. And so SVM can be memory efficient. And when I say memory efficient, don't get me wrong. Of course, the linear regression model is going to be a lot more memory efficient. But this one, compared to KNN, remember, KNN was a lazy algorithm. So when you throw a new data, it has to go through the entire data set in the train set and do the math. But the SVM only goes over the support vectors in the future repetitions, right? When you throw a new data set, if you want to classify it, it only goes through support vectors in the train set and then give you what the class is. But in KNN, if I throw a new data set, new test set, the model has to go through the entire train set. So for that reason, we say, okay, SVM is more efficient, memory efficient than KNN. Do not confuse this memory efficient with the speed of the model, right? Because when the data set is large and the dimension, even when the dimension is slow, SVM is going to be a lot slower. Okay. All right. Then SVM can handle nonlinear data set perfectly. So I think this is one of the main advantages of the SVM. How beautifully it can handle nonlinear data. It can handle high dimensional spaces. And this is definitely the big advantage of SVM over KNN, because it can beautifully, using that RBF kernel, it can force many of those dimensions to go to 0. We didn't talk about the mathematics here in this class, but intuitively, it's going to force many of those alphas to go to 0. So it's going to shrink the dimension beautifully. So it can handle high dimensional space, even when the dimension is greater than sample observation. So this is really, really important. In KNN, this cannot happen. It is used both for classification and regression. It's not very sensitive to overfitting. Again, this depends. You know, linear SVM is sensitive to overfitting somehow. At least MMC is sensitive to overfitting. We talked about that, right? But SVC or SVM in general, the regularized version using the soft margin, is not. It can handle, well, usually it has high accuracy. You saw the performance of the model when we were using the RBF kernel, right? So the model was doing a decent job. What are the disadvantages? So there's no probability outcome there. So that's the main, I don't want to call it main disadvantage, but if you want to do interpretation, you use econometrics, you don't use machine learning. Okay, just keep in mind. If you want to do policy analysis, you use machine learning as a, I don't know, as a backup tool to make sure that your models your econometric model is in check or not. So that's how you should use a machine learning model. Otherwise, for policy applications, you must do something interpretable. Long training time when we have large data sets. So this is a very big disadvantage. But So let me give you a separate discussion. So how we're doing in terms of time. Okay. So historically, SVMs were extensively used even for image recognition, right? Even for text mining and things like that. But then after the neural networks became popular again, now people we're using, for example, CNN, convolutional neural networks for image recognition. No one, or at least barely people use SVM for image recognition, okay? So the idea, the problem is that for both of them, the training time is large. Both the neural networks or the SVM, the training time is large. But if the problem is the training time, and then you are going to work with a model that is going to give you a better performance, which is neural networks compared to SVM, okay? So historically, it was the tool for even image recognition, but nowadays it's rarely used. And because the training time is going to be super, super, super large. And image recognition data sets we're talking about millions of records. So for that reason, SVM is not used. And if you want to pay the cost of computation, you better work with a model which with performance better. Because we don't talk about, maybe in the very last class of this course, I will give you a preview of the deep learning and why we should go beyond the machine learning models. Because deep learning is super flexible. You can approximate literally anything, any functional form using neural networks. That's called approximation theorem. Okay, the other disadvantages of SVM is limited interpretability, especially for kernel SVM, so we cannot, especially for RBF. So the coefficients that are forced to go to 0, you have no idea. You can control them literally, but when it comes to interpretation, they're lost, right? And does not perform well with noisy data. However, guys, remember KNN was awesome. KNN was really good, right? With noisy data, KNN, especially if you put K to small numbers, it can easily find those noises, right? But is it a good thing? Not necessarily, right? Because you want your model to learn the patterns from the true relationship, not the noise. Not learning from noise is not a good thing. And it's suited for, so this is also, you have to pay a very good attention that if your data set is large, SVM is not necessarily your best answer. And you don't need to work with neural networks because that's also painful. So the answer for very large data set, at least for this course, is going to be random forest. Okay, so we're going to talk about random forest in 2 weeks. Oh, and the multiple versions of the random forest. Okay, so let's finally talk about the applications in finance and conclude the class. Corporate financial statements and bankruptcy. So at the end of the day, you want to say if a company is going to go bankrupt or not. But usually you have to consider, you go over the financial statement, there are hundreds of ratios out there. I think for those of you who have taken fixed income or courses with Paul, you know that there are hundreds of ratios that you can think of. So the data is high dimensional. When the data is high dimensional, SVM, and the data is also small size because look at the ratios, they're quarterly reported. Even if you go 100 years back, 400 observation, that's it. Okay, so the data size is small, the dimension is large. So for that reason, SVM is going to do a decent job. And you can identify stressed companies, and stressed companies are the ones that are close to bankruptcy. And usually hedge funds are targeting those companies. And then it's a good thing, you know, they're short sell those companies and then force them to go bankrupt. So again, here we are going to use many fundamental and technical features. And sentiment analysis. It used to be, SVM used to be, I think, used a lot more in industry, but now people are doing neural networks for sentiment analysis because it's more powerful. But regardless, you can think of, you know, give it a try. You know, you can think of, if you want to use machine learning app model, you can try SVM. And sometimes surprisingly, it may outperform. So you have to compare relevant models with each other, right? And money laundering analysis, spam detection. So these are all classification examples, right? And as you can see, when it comes to applications in finance, usually it's the applications in KNN, SVM, logistic regression. These are classification applications. Loan management. So we look at a bunch of examples in the loan management, right? All right, so I think I'm done. The appendix goes over, this is maximum margin classifier solution. We talked about that the beauty of SVM is that when there is solution, the closed form solution, you have a formula for closed form solution, right? So for example, MMC is not necessarily feasible sometimes if the data is not linear. So we do SVM. SVM is based on, the answer to the SVM is based on this optimization problem, right? This is a convex optimization problem. And as you can see, there are beautiful closed form solutions for that. At the end of the day, you can mathematically apply this thing and then calculate the W stars. All right, so the idea is that this is your optimization problem. You take the Lagrangian from both sides and you take derivative with respect to parameters that you're optimizing, W's and B, and set it equal to 0, and you can solve for the closed form solution answer. All right, so here are the questions that you had on the quiz. So let's see if you can answer them together. You should be able to answer all of them now. So what does non-separable data mean? Do we have the answer for that? So we know what do we mean by non-separable data? Okay. Does the kernel function act the same way as a standardization conceptually, whereby the data is scaled up, but the distribution of the data does not change? So what's the answer to this one? Abraham, can you answer your own question? It is good to have someone that can ask good questions. So this is a good capability. So basically it says that, do you think that this kernel this mapping function, this kernel function is doing the same thing to the data as the standardization? The answer is that these two are completely different beasts, right? So kernels are just, for example, RBF kernel is calculating the distance of the observations from each other. It has nothing to do with the distribution of the data itself, right? Just remember, do not confuse these things. Number 3, when do we use MMC versus SVM? The answer is we always use SVM. And one of the, so for example, if in SVM, we are doing grid search to find a best hyperparameter, right? If I do linear kernel, and if I set, for example, somehow play around with that C such that I'm not allowing for any kind of misclassification, make it a hard margin. So that's going to be MMC, right? So we're going to always use SVM. And then finally, 4, even after using the kernel trick, does SVM perform faster than KNN on average? So this really depends on the size of the data set, right? If the data set is like the one that we worked on homework 6, bike share 17,000 observation, KNN is a lot faster than SVM. All right, I think we're good. So I give 5 minutes back to you. I think cumulatively, I owed you 5 minutes, so here you go. All right, guys at home, do you have any questions for me? You're good. So we'll stop here.